Hello friends, in this video we are going to discuss from recurrent tree to two-dimensional dynamic programming. The problem is buy best time to buy and sell stock for. We are given an array represents the price of the ith day. We need to find the maximum profit with k transaction. So before solve this problem, you should have been solved number 3, number 2, and number 1 here. Firstly, let's take a look at number 2. For number 2, you can make as many transactions as you want. So the problem is very easy. As long as you can make profit, then you make transaction. So the total profit is the maximum profit you can get. So for number 3 is a special case of number 4. In number 3, you allow only 2 transactions. So let's take a look for k equals 2. The recurrent tree, we start from index 0. In this example, k would be terminated at 1 instead of 0. So if we can make profit, because this picture here initialize k is 3. So for 2 transactions, we just make the tree terminated at k equals 1. Okay, so each step, if you make transaction, you can make profit, then you have the option 1 to use one transaction, and the optional 2 you don't use that transaction, which means you just keep going. So for example, we start from index 0, then we move to index 1. If we make transaction, we can get profit of 2. Then we got a sub problem here. We move index to 2 because we ended at 1. So next we move to 2 with k is 3 minus 1 is 2. If you do not use that transaction, which means you keep going, so you move index to 2, then 8 minus 3 here, minus 3 is 5. You can make 5 profit, and next you move index to here, then you get this sub problem, and if you keep going, you get this sub problem and this sub problem. So for each sub problem, we doing the same. Then we terminate at k equals 1 here. We can use DFS or BFS to solve this problem. Let's take a look at our DFS solution. Here I initialize at with k equals 2. Then we terminate at k equals 0 in the code, or we terminate when the here is a little problem. The index should be 0. So we terminate either k is 0 or we reach the end of the array. So we return 0. Otherwise, we keep tracking minimum price. Then the maximum price, the maximum profit we can get is price I minus minimum price we already scanned. So if this larger than 0, which means we can make some profit if we make transaction. So our profit would be this one plus the rest of the array. Here is rest of array with k minus 1 transaction. If we do not, this is optional 1. Optional 2, you do not use that transaction, you just keep going. So the final answer is the maximum transaction. In this tree here, the maximum value would be 4 plus 5, which is 9. So that's with most 2 transactions. Here is our BFS solution. BFS solution, we start from here. Max profit 0, index 0, k is 0. We push this node into the queue, and when queue is not empty, here optional 1. Optional 2, we just keep going here. So first step, we push this, we pop out this, push those into the queue. We got profit with this one, and this one. Then next, we will pop out this from the queue. We will get this one. That's the while loop does. If the node of the k equals k, or the index reaches the end of the length, then we should terminate. So that's our BFS solution. For k is 2, the time complexity would be n square. So because this tree, the height of the tree is only 3, it is not too large. Now we can move to problem number 4. We can move to problem number 4 with at most k transaction. With at most k transaction, we just doing the same when the k reached 0, the same as DFS. For example, here k is 3, we start from index 0 with k is 3, and the first step we are here, we can make profit of 2 and get subproblem here, which means the subproblem is here with k is 2. And if we do not use that transaction, we just keep going, we move to here, we get profit of 5. Then next subproblem would be start from here with k equal to 2. So as you can see here, if the input is very large and k is very large, we get a lot of the same subproblem. This one here, and this one here, and this one here. This remind us we can use memorizing. To reduce time complexity. That's our DFS cache solution. Here is our DFS cache solution. This node here remind us it's gonna be a two-dimensional k and the length of the array, that's two-dimensional. We initialize with this -1. Here is the same as version 3. When k is 0 or 1, we reach to the end of the array. If k is larger than the rest of the array, then this is problem number 2. We just call that function. Otherwise, if we already know, we just return directly. So here is our optional 1. Use that transaction, we can get the profit, for example here, and plus the maximum profit of this subtree. That's this statement. Or if we do not use that transaction, we just keep it going. So at the end, we will get the final answer. For this example, k is 3, we get maximum value of 5 plus 4 plus 2, then ended here. So that's 11. Again, for every DFS with memorizing top-down solution, we can convert it to a bottom-up dynamic programming solution. For example, we initialize here. When k is 0, of course, no matter how many days we do not make transaction, we get profit of 0 here. And if we only have one day here, it doesn't matter how many transactions we can make, the profit we can get is 0. So this initialized status just the same as termination status here. The same. Now let's take a look. We start from here, index 1. The best value we can get is 5 minus 3, which is 2. If we make transaction, we get 2. If we do not make transaction, we get this one. We get 0. So maximum of those two values is 2. Then we move to next 8. We move to here. If we do not make transaction here, we can get is 2. We do not make transaction. That 2 comes from here. If we make transaction, we have 2. Then we get 8 minus. It depends which day we buy. If we sell at 8, if we buy here, we get 3. And if we buy here, that's 8 minus 3. Well, if we buy at here, the value, the profit, we should plus the previous with one less transaction, which is here. That's the previous profit we can get is 0. And also, if we buy it here, we should use 8 minus 3 plus this value here, 0, which is 3, which is 5. So here we get 5. Now we keep going to fill this table. Here we get 5. Here and here, if we do not make transaction, we can get 5 comes here, 5. If we make transaction, the best value we can get is we buy it here, we get 4. Then plus with one less transaction, which is here, 4 plus 0 is 4. So here is 5, 5, 5, 5. We can fill this table. So let's take a look at the next step. Next, we can fill another row. So we know here is 2, 5, 5, 5, 5, 5, 5. Now we go to k is equals 2. Here, if we do not make transaction, we get 0. If we make transaction, the value we can get is 5 minus. The only option is buy here, buy at day 0, buy at day 0. So it's 3 plus the profit we already have and at day 0 with one less transaction. So it's 0, it's 2. So here is 2. Then we move to here. If we do not make transaction at here, the best value we get comes from here. It's 2. If we make transaction, the best value we can get, the first option is we buy it here, we buy at day 1. So the profit we can get is 8 minus 5 plus the profit we already have here, that's 2. So it's 5. Or we buy it here at day 0. The best value we can get is 8 minus 3 plus one less transaction is here. So that's 0. We plus 0. That's 5. That's 5. So if we keep going, here is 5. Now we are here. So if we do not make transaction, we get 5. That comes from here. If we make transaction, the best value we can get, we just try. If we buy here, the price is 1. So 5 minus 1 plus the value we already have, the profit we already have, it comes from here. The same day, but with one less transaction, is here, is 5. So that's 9. Or you can buy it here. That's 5 minus 8 plus 5. So we just try this one, and we know the best value is 9 here. Okay, I just moved the page a little bit to the left. So as we keep going, we fill the table, we get 9, 9, 9 here. And let's take a look the code, the first version of dynamic programming. Firstly, we fill the array with 0 by default, and we start with n minus 1 to k. That's the loop going this way, and for each day we start from day 1. We start from here because day 0 is 0, we already initialized. Then we look backward. For example, we are here, we are day 4. We should try each previous day. The maximum profit is if we do not make transaction at that day. That's the previous one we get if we do not make transaction at that day. For example, here, if we do not make transaction here, the maximum profit we can get is 5. Otherwise, we try every possible. We're going backward. The profit we can get is the price of this day, minus each of the previous day, the price, then plus with one less transaction. For example, here 9, we should use 5 minus 1 plus with one less transaction. Here we just try every possible value to get the maximum value. So that's our first dynamic programming version. At the end we return this one. Now if you take a look here, this is 9, this 9. If you use you see here this is 9, and this 5 this 5 this is 1, this 9 equals 5 minus 1 plus 5. This 5 comes here. Okay, to get the maximum value of this here, the optional one is do not use transaction. So we get here another option. If we look at this statement here, we just use this one minus this one, or this one minus this one, or this one minus this one, or this one minus this one. We look backward for each of this, and we pick the maximum value of this one minus this one, this one minus this one. So the maximum value is 5 minus 1 here, 5 minus 1. If ending at here, the value would be 5 minus 8 plus 5. Plus 5. That's the day if we sell at that day, we get 5. So this reminds us we don't have, each time we don't need to look backwards. We can eliminate this for loop. Each time we just keep tracking the max value of the previous value. Here is our version 2 dynamic programming. We eliminate that for loop. We just keep track the max value of the with one less transaction minus the price of that day. For this example, we just keep tracking 5 minus 1, 5 minus 8, 2 minus 5, 0 minus 3. The maximum value of this is 5 minus 1 here. Then plus the price of this day is 5. That's the maximum value of the profit we can get. So let's use this to fill this table. Here, the maximum value, if you do not make transaction, is 0. If you make transaction, you get 2. Here, if you do not make transaction, you get 2. If you make transaction, the maximum value of here 2 minus 5 is 2 minus 5 is minus 3. 0 minus 3. 0 minus 3 is minus 3. The maximum value is minus 3 plus the price if you sell at this day is 8 you can get. So you get 5 here, and here we move to here. We move to here. If you do not transaction, you get 5. If you transaction, the maximum value of previous 5 minus 8 here, 5 minus 8, 2 minus 5, 0 minus 3. This is minus 3, minus 3. This is minus 3. Plus 1. All of them is 4. So 4 compared with 5, the max value is 5. So we keep going. We keep going. Here, do not make transaction is 5. If you make transaction, the best value is 5 minus 1, which is 4, because one of those we already know is minus 3. So 5 compare with 5 here, 5 plus 5 minus 1 is 9. Okay, this 5 comes here if you sell at this day. This 5 minus 1 comes here, 5 minus 1 here, So you get 9. So we keep fill the table, we'll get 11 here eventually. So that's our second dynamic programming solution version. We don't have to look backward. Again, every time we say here, when we try to compute n, we use previous result n minus 1, which means we don't have to save all of the result. We just need to save previous result. This is our another version. We reduce the space complexity to order n here, order n. Each time we can copy fn2 to fn1. So next time we use fn1, the previous result. Or we can swap those two objects, the reference of two objects. A better solution, we flip index each time. We flip. At beginning, this is 1. It will use f of 0. This is 0. Then next time we flip it to 0. Then we reduce time complexity to order n because we ignore the leading constant. Okay, that's it. Thank you. Oh, here is 11. Here is 11 because we can make profits 3 minus 1.